along with that packet I just showed you, that's the main bank of material for test 4.
Yeah.
Oh, it's already after 62.
We just got you 2 stone tiles.
It's just, the end's almost here. And I don't know about all of you, but this semester is just kind of slowly going. Ever since the litany of snow days that we had, yeah.
And then spring break.
And then, yeah, the extra break that we had. Winter break and then a late winter break, known as spring break. So, test format, this has been typed up a little more neatly than this and posted on our D2L page with test 4's material, but it still has the same distribution of problem types. So, in preparation for the test, which is Tuesday night, in here, I'll get in here at 5 o'clock if there's any last minute Q&A you want to go through, so that's a little bit earlier than usual. And then we can start the test at 6 if you want to, 6 till 8 or 8:30 or however long it takes you to do it. But there will be 10 proper problems, stopping with the surface area topics we talked about on Tuesday night of this week. What I want to show you tonight is surface integrals and maybe flux. If I don't show you a flux problem, I can tell you what flux is, what it measures. But this would only relate to one problem on the test, a bonus problem involving a surface integral of some sort. And since we focused so much on parametric surfaces this past Tuesday, and just because they're so freaking cool, I'll probably lean toward a surface integral involving parametric surfaces as the bonus problem on the test. So any kind of problems you want to see, I mean, this is kind of our last, well, this is our last contact hour before the test night. How far have you gotten with the material, dare I ask?
I haven't even printed it all out yet.
Haven't even printed it all out yet. So you started in so much that some ink has been, spread onto white paper and you've seen it. Okay, pencil to paper hasn't happened yet. Okay, you're about to ask a question.
Yes, that's the 4th at 6 here.
No, the 4th is Monday. The 5th is Tuesday. Yeah. So Star Wars Day is Monday. May the 4th be with you. Yeah. And then May 5th is Tuesday next week. Yes, sir.
Like anything past line integrals, because I don't know anything.
Well, you were here for that night.
I
Okay.
was here for line integrals. I wasn't here for any of the other stuff.
The kind of, I guess, triple integral problem you could expect, well, just sort of giving it all a once over, okay, just for everybody's benefit. The kind of triple integral problems you can probably expect for the one that's represented there, just turning back to the supplement here on triple integrals. It would most definitely be one that gives you a graph of a surface like this and asks you to determine the limits based on whatever the solid looks like. It could be a volume problem. See, these 4 problems here just find the volumes of these solids by using a triple integral, okay? And for volume, what is your triple integral integrand if you want to find the volume of a solid?
1.
1. Yeah, if you do the triple integral of 1 in XYZ coordinates, it's guaranteed to give you just the pure volume of the solid you're integrating over. So with a graph like this, choose your Z limits and then flatten it to the XY plane, choose your X and Y limits, and then set up that triple integral to calculate your volume. Okay. One problem there. I mentioned one problem of each from spherical and cylindrical coordinates. So,
can we just do like one of each going down the list?
Pardon?
Can we just do like one of each going down that list?
Going down the list.
The ones with the dots.
Oh, you mean an example of one of each, or just okay? Well, okay. So we'll go back to the triple integral XYZ. Here's a picture that I actually got from Danielle, a problem that she had found. And if you had to calculate the volume of this solid, I'll probably give you a computer-generated image for the test, but it's bounded below by the XY. It's all in the first octant. Everything here is where X, Y, and Z are positive. The bottom is the XY plane. This curved lateral surface comes from this parabolic cylinder. And remember, cylinder isn't always, a paper towel roll. It's any two-dimensional curve that runs parallel to the Z-axis or any axis. So this is an example of a parabolic cylinder because it comes from this parabola shape running parallel to the Z-axis. So that gives you a lateral side to the solid. The back there is a flat rectangle. This side over here is just a triangle. And then the top, the roof, is based on the equation of this plane. So when you're looking to determine your limits, if the limits are not already ascribed for you, what you want to do is make sure if you choose the Z direction first. I tend to try to the Z direction first Just imagine drawing a vertical ray through this. And any vertical line you draw, will it have the same entrance and the same exit if it pierces through this solid? It's going to enter where?
The bottom.
The bottom. And okay, so since we're going in the z direction, give me the z value where it enters.
0.
It enters at z equals 0. It exits at
Z
not z
9
equals 9.
minus y.
Because right here z isn't equal to 9. Its exit is a variable surface.
Z.
But the definition is in terms of z. Z being in terms of y like this. So it enters at z equals 0. It exits at z equals 9 minus y. So if you set this up as a triple integral, your z limits would begin at 0 where it enters, and it exits at z equals 9 minus y. Okay? And so once you've done the z direction, how do you determine the remaining two limits?
Flatten.
Yeah, always diminish the dimension that you just took care of. In other words, flatten it in terms of the z direction, the z dimension, flatten it to the xy plane. And if this flattens to the xy plane, you know, since you're in the first octant here, you only need to draw the first quadrant here. Notice this has an x-intercept at 81, has a y-intercept at 9, and so this should be a parabola that's opening along the negative x-axis direction, looking something like this. And you can still use the same curves. You know, this equation here still comes from that. And when I diminish it to 2 dimensions, that's still the curve x equals 81 minus y squared. So which order would you choose for your middle? Would you do the y direction next or the x direction next?
Okay.
We'll go with the next term.
Did you say k?
X.
Oh, x. I thought you said k. Is that
Yes.
either asking me a question or you just, you know, a little potassium? So yeah, I would do the x direction next. But some of you said y. Now let me sort of, you know, eschew the obfuscation. If based on the way this equation is set up, it's defined as x equaling, you know, a curve in terms of y. So if your boundaries, and you could do the y direction, you could enter here at y equals 0, but you exit at y equals what? And see, there's the rub. It's not much of a bad rub. You just have to solve this for y in terms of x. But then you introduce a square root to one of your limits. And if they're avoidable, just avoid the square roots. That's why I would leave this as x equals 81 minus y squared and commit to doing the x direction next. If you go in the x direction, you've got a consistent entrance and exit, no matter where you draw that x direction ray. You enter at x equals 0, you exit at x equals 81 minus y squared. So that's why I would recommend the x direction next. You could do y if you wanted to, but you're just going to have to solve this for y. Y would have the square root of 81 minus x. And maybe that's not too bad for the integration. You have to wait and see. But then what do you commit for your y limits when you're finished?
0 and 9.
Yeah, so we diminished the z dimension from 3D to 2D. Now we want to diminish the x direction from 2D to 1D. And then those limits there that are left over, that represents your constant limits for the y interval. And so that would be the setup for that particular volume problem. And then actually evaluating it, integrate z. You're integrating 1 with respect to z, so that just goes to z. And then you enter those limits. That gives you 9 minus y. Then you integrate this with respect to x. Keep in mind you're doing partial antiderivatives. So both 9 and y are constants with respect to x. They should become 9x minus, well, xy. And you want to plug those limits in for the x variable that you just integrated. So the only non-zero contribution comes from that top limit plugged in. 9 times 81 minus y squared minus y times 81 minus y squared. And then take the liberty of simplifying it before you go to your last integral, just to see what your term by term is. 729, that's maybe? Oh, hey, look at there, 4 non-like terms. So now you get to integrate this from 0 to 9. So you get 729y minus 3y to the third minus 81 halves y squared plus a quarter y to the fourth And then the rest is just careful plugging with 9. Okay. I'll pull the QED card, which Jonathan Lamb apparently is very fond of doing. Have I done that with you yet?
Quite easily
Hey, do you know what QED means?
Quite easily done.
Not quite easily done. Okay, yeah, quite easily done is a very good. It's not exactly a literal translation, but it's sufficient for our purposes. You know, synonymous. Yeah, it just means, you know, something we've already seen. You know, it works the same way. Quite easily done. I actually think I may be stealing that from you, because pronouncing it in Latin always sounds pedantic and showy. But that's, if you ever see QED, it's basically the teacher saying, "You've done something like this before. You should be pros at it." Okay, you should be pros at it.
Not pros at it.
It's like I said, pros at it. Yeah. Okay, you should be pros at that by now. All right. Quid erat demonstratum is what it actually stands for. If you ever had that on, you know, your final Jeopardy category. So, trivial integrals, x, y, z, something like that, where you're calculating the volume of a solid, where the graph would be provided for you. Okay. Trivial integrals in cylindrical versus spherical. Okay. What lends itself to spherical coordinates? And keep in mind, well, first off, big point here. What is the cylindrical coordinate system? What does it consist of?
R theta z.
R theta z, exactly. It's polar coordinates. Polar is technically 2-dimensional, but if you add the rectangular z with it, it becomes a 3-dimensional or cylindrical system. So it's really just polar plus z. So looking for things like x squared plus y squared, that still translates to r squared in cylindrical, just like it translated to r squared in polar. The translation for z is just z equals z. That's it. Any use of z stays z, but x and y's can use their r cosine theta, r sine theta translations and things like that. So cylindrical kind of lends itself to things like paraboloids. The equation of a paraboloid is z equals x squared plus y squared. Cones, z equals the square root of x squared plus y squared. Any use of that x squared plus y squared thing works really well with polar, also works well with cylindrical. Spherical coordinates. What are the actual 3 coordinates used in the spherical system? Well, the Greek are rho. I guess it's the Greek r. I guess rho, theta, and phi. Rho is like a 3-dimensional version of the 2D r in polar. Polar is down here flat in the xy plane, so it only goes like this radially. Rho is a 3-dimensional radius, like the explosion of, you know, fireworks you see on Doomsday or something like that. So rho goes omnidirectionally out of the origin, like the radius of a sphere. So if you're dealing with a sphere surface, the sphere x squared plus y squared equals 25 is a sphere centered at the origin with radius 5. In spherical, that will become the equation rho equals 5. That's it. So any constant value of rho represents a sphere in 3 space. What's your angle phi represent? Inclination. Be careful, because inclination you're thinking of doing like this. And I'm sorry if that looks like that. Yeah, you kind of want to think of it. Yeah, but it's actually I guess inclination off the z vertical axis.
Wouldn't that be declination?
Well, so
declining?
Declination, yes, since you're going down like that. The phi value 0 is always the North Pole, and phi only exists from 0 to pi. So you can't use negative values of phi. You can't use phi values that are greater than pi. So if your positive z-axis is up here where phi equals 0, then going any direction off of z by whatever phi's angle is really considered in all directions. So phi equals pi over 4 would be essentially any point that's 45 degrees off the z-axis, making a cone like that. Phi equals pi over 2 is essentially the xy plane, because you're 90 degrees off the z-axis. And phi equals pi will be the south pole. So you kind of need to think of phi as, like, when you're looking at a globe and you have the different lines of latitude, technically, I guess 0 latitude is really the equator, isn't it?
Yes.
And then 90 latitude north would be the North Pole. So it's not that. The way phi works is 0 for phi is North Pole, and 90 for pi is the equator, and 180 for pi is South Pole. For phi is South Pole. Okay. Theta, same as polar. Theta is just your lateral spin. You know, I also made the analogy of a joystick. If you spin your joystick like this, that's rotating in terms of theta. If you tilt your joystick, that's declinating it with respect to phi. Yeah. And the length of your joystick is your rho, because it represents the radius of this sphere. It's not that. So, an example. Let's pull this up. Oh, sugar. Blow it up. Okay. What about this number 11? A sphere of radius 12 has a portion cut away from it in the shape of a cone. The cone makes a 60-degree angle with the z-axis. Determine the volume of the solid remaining after that cone has been cut out and removed. So the cone cuts all the way to the center of the sphere. It's bored out, removed, and you're looking for the volume of the remaining. So this is a solid. Unlike Tuesday night, we were dealing with surface areas of spheres. See, that's just a two-dimensional measure of the surface area with a surface integral. But in this case, you're going to want to use spherical coordinates, most likely. Well, what lends itself to spherical coordinates here? Sorry for the duh question, but it's kind of a duh question.
Because you got
The fact that it's a sphere. Yeah. So, yeah, if you're dealing with a sphere, any solid part of a sphere, you know, shift gears to spherical coordinates. So if I set this up as a triple integral, in XYZ coordinates, it would be the, well, I guess I should say region D or something. The triple integral integrating over this region D in space of the function 1, and then dv would be dx, dy, dz, dz, dx, dy, you know, one of those 6 orders. But since this lends itself to spherical coordinates, okay, what is your integrand going to become? Let me see if anybody remembers that. It was given to you.
Rho squared sine of phi.
Beautiful. Yes. The integration compensator, aka Jacobian, if you want to know the proper name of it, the integration compensator going from XYZ coordinates to spherical is rho squared sine phi, and that is given on the test. The conversions for cylindrical and spherical will be given as a formula sheet on the test. Well, duh. It's open notebook. Look at it myself. so yeah, you had to at least have that rho squared sine phi in there. That's what the 1 becomes. So you can't have just the 1 inside a spherical integral. Just like a polar integral or a cylindrical integral, your minimum integrand is always going to at least be r. Same thing for spherical. Your minimum integrand is always going to be at least that rho squared sine phi. Okay. Then we want to set up limits. Most often, I do rho first, just because it represents your sphere radius, and then theta and phi you can do interchangeably. It doesn't really matter. I guess I'll do phi next, since there's a proper function of phi in here as part of the Jacobian. But then, what would your limits need to be for rho, since it's the inner integral? You're giving me phi. Yeah.
Would that be root?
Rho is the radius of the sphere.
Root 12 or root 12?
So, see, in
I think it would be 0 to 12.
it should be 0 to 12, because the way you do, see, in 2 dimensions, when you're dealing with polar, you always start from the origin, and r goes outward like this from 0 to 2, or whatever the radius of the circle is. Rho is like a 3-dimensional version of r. It goes omnidirectionally.
So it goes from
And
0
I'm not sure
to
if that's a
every
word, but it
radius.
goes in all directions from the origin outward. So if you imagine, like, you know, the origin's here where this little apex of the cone is, if your rho comes out through this solid in all directions, it's going to start at rho equals 0, the center at origin, and then come outward
To whatever your radius.
to whatever your sphere radius is. Yeah, so the radius of a sphere needs to be permanently synced up with the value rho in spherical coordinates. So yeah, no matter what direction you go through the solid, even if you're on the edge of that cone, rho goes from 0 to 12 here, 0 to 12 there, 0 to 12, 0 to 12 this way, whatever the way you're, you know, coming out in 3 dimensions. So the radius of the sphere always represents your rho limits. And since it's a solid sphere, you know, you're doing a volume, so you're including the stuff on the inside, rho continuously changes from 0 to 12 to the outer radius. Okay. If we had an inner sphere that cut out a core of radius 6 that was void, and the only solid part was this, you know, between the radius of 6 and 12, what would that change your rho limits to?
6 to 12.
Yeah, so if it was a concentric sphere hollowed out of the middle of radius 6, you change your limits from 6 to 12. Okay, and you probably had to have some kind of dotted picture here to let you know that there is a spherical core cut out in addition to the conic, the cone-shaped core. So now, those phi limits, please, sir.
Oh, pi over 3 pi.
Yes. Phi equals 0 is here. You're given that the part that's taken out of the solid is 60 degrees off the z-axis. So from here, from 0 to pi over 3, there's nothing for phi. Phi technically begins right here at pi over 3, and then continues through pi over 2 all the way to the south pole at pi. So your proper limits for phi that represent where the actual stuff is from pi over 3 to pi. Theta.
0 to 2 pi.
Yeah, theta is your lateral spin, so, you know, going in this direction. And the only real qualifier that needs to be mentioned in the problem or the picture is if it says first octant. First octant would be theta going from 0 to pi over 2, because it's like the first quadrant in XYZ or XY plane. So, I mean, the only other thing I can imagine affecting it is if this says, you know, if y is greater than 0. So the negative y-axis half will cut away. That would be from 0 to pi for theta, because that corresponds to here, 0 to pi is where y is positive, so that would, you know, mimic that in 3 space. But in this case, the whole thing is there, all the way around at least. So you'll be using 0 to 2 pi for theta. And notice, most every integral I've ever done in spherical coordinates has been an integral that has constant limits when you get to setting the integral up. If you got constant limits and your integrand can be factored in terms of the functions you're dealing with, remember that same trick I showed you earlier with double integrals applies to triple integrals too. You can do the 0 to 12 limits for your rho, or your function of rho, which is rho squared, times the pi over 3 to pi limits for your phi function, and then times, well, technically, times what? What's left? Yeah, you're integrating 1 with respect to theta, so really it's always going to give you that if you're going from 0 to 2 pi. So if it's factorable, and if the Jacobian's all that's there, it's factorable. You can split it apart, and then apply those constant limits one at a time, and then multiply the result together at the end. So whatever this is, 12 cubed divided by 3 times negative cosine, so negative cosine of pi is positive 1, minus negative cosine of pi over 3, which is 1/2. So that contributes to 3 halves to the mix. And then times 2 pi. And then simplify. QE. I think I did that right. Negative cosine. My confidence is shattered. Negative cosine of negative 1 will be positive 1, minus negative cosine of pi over 3.
And conveniently, we draw 3 halves, which 1 plus 1 half equals cancels with the 2 over 3.
Boom and boom. So pi times 12 to the third. Wow. 12 to the third, I have not committed to memory, so arithmetic, definitely QED. Okay. Thank you. I never became the human calculator. I never learned those cool human calculator tricks. Just because I honestly, I sucked at arithmetic. Okay. So one of each type, a cylindrical. So let me pull up a cylindrical example. And they really lend themselves to pictures. Okay, or if not a picture, one like this second one here. You're asked to convert this integral to cylindrical. You're integrating over the region over the region D in space, and D is given. There's a description here, and once again, if you're setting up limits, either you know, double integrals or triple integrals, pay very careful to that very special part of speech that helps you envision things, you know, with locations in space. Okay, the integration region here, the region D, is the region between. So there's something between the plane z equals 1 and z equals 4. So just that, z equals 1's here, z equals 4's there. So that's an infinite chunk. Hopefully there's something that's going to, you know, further narrow this space down. So it's between those 2 planes and lying inside, so that gives you another locative, inside the cylinder x squared plus y squared equals 9. What does that region D look like in space? Okay, a pretty thick disk. But kind of a disk, or maybe a really thick hockey puck. Z equals 1 is here. Z equals 1 is parallel to the xy plane, because the xy plane is z equals 0. So z equals 1 is 1 click higher. Z equals 4 is up here. So that's 2 parallel planes. And then what does this look like in space? On the xy plane, it's a circle of radius 3. But in 3D, Yeah, since the z variable is gone, that means it's a circle in the xy plane of radius 3 that's wrapped around the z-axis infinitely. So z equals 1, cylinder, not a cone. It's a paper towel.
I said a column.
Oh, a column. I thought you said a cone. Sorry about that. Yeah, so you're between, hey Dave, you're between z equals 1 and z equals 4, okay? And then you're inside this lateral paper towel roll of radius 3 wrapped around the z-axis. So it's kind of like a can. Paint can maybe. Okay, a very thick disc. But yeah, it's got a height of from 1 to 4, so the height's 3. That cylinder's on the outside, so it makes a proper, can. Yes?
Not solid.
It is, because it's the region bounded between the planes and inside the cylinder. So your triple integral region is always going to be a solid in 3 space, not just the boundary, but the guts inside too. So it is the cylinder on the outside, the planes on the top and the bottom, and all the stuff in the middle. And what's the best order to do first? And keep in mind, cylindrical is z equals z, and then r's and thetas. So
R theta.
okay, so the usual order I almost always ascribe to a cylindrical integral, and it's rare for me to ever even see a different integration order than this, is to do z first. Since if you go in the z direction through this region, even without a graph, what is your first z limit going to have to be upon entering?
Or 1.
Be careful, yeah. It's between z equals 1 and z equals 4. So the first z limit should be 1. And then the last z limit should be 4. Now we do have a proper non-unit integrand here. We have to translate this too, but that works pretty well with cylindrical. We'll do that last. Okay, now we've done the z direction. And since we are committing to cylindrical here, you got that. Don't forget the extra r. The same extra r you need for polar and 2D is still present in cylindrical and 3D.
So the Jacobian is just an R, nothing fancy.
Just nothing fancy. Not as fancy as spherical. Just that same extra r.
So it's e to the r squared.
So that will be e to the r squared would be your integrand. And so thank you. Times r. And see, that works. That's the smoothest use of ever. If u equals r squared, 2r dr, by the time you get to integrating that, that's the best chain rule reversal that there is. We'll get there though. Okay. What about your r and your theta limits? Where do you get that from the picture of this solid?
Your r is 0 to 3, right?
Yeah, because now that we've done the z dimension of this can that's kind of floating in space from 1 to 4, flatten it to the xy plane. Because even in determining your limits, you can diminish one dimension at a time. Now that you've diminished it down, all that's left, the shadow of that can, when you project it to the xy plane, is still lying inside the circle. So now you have a filled-in solid circle of radius 3, and that lends itself to 0 to 3 for r. And again, no extra qualifiers about first octant or anything like that. So if that's missing, your theta goes from 0 to 2 pi. Okay. So it could be some kind of volume problem, or some translate from rectangular to cylindrical, or translate to spherical kind of problem like that. Okay. But I think for convenience, I'll probably still put the conversion formulas on the test, just so you don't have to shuffle through your notebooks to get to that. ¿Preguntas? ¿Hay preguntas? No hay? All right then. Okay, we're catching up, Kai, to what you were curious about. Vector fields, it's essentially going to be kind of like a matching problem. You'll be given, and that's kind of like the very first problem on the packet. Now, feel free to jump into the textbook. You want your test back, don't you?
Oh, that'd be great. I wasn't going to say that though, but this, so I've never seen this before in my life, and then you brought it up in this class and everything, and then the other night, maybe
Where the heck
2 nights,
is it?
No,
So-
2 nights ago I was watching the Science Channel, and they were talking about tsunamis, and they had these, these vector.
Oh, these things? Well, yeah, I mean, just
under the
most,
water
anytime
showing the
you
wave.
hear of severe weather coming,
Yeah.
or there's like a cold front coming through, or
Right.
some kind of, big, nor'easter
so
coming
that's
through or something like
specifically what
that.
they
Your
use
meteorologist
right
usually
there.
projects things like this, based on the weather flow from, Montana down through Kansas, down to where we are and stuff like that. So yeah, you see them all over the place. And some of you have seen these in differential equations as slope fields. Kind of like slope fields. A little bit different, but still a bunch of lines out there in the plane. But this is the way the matching problem would look like. I may give you a few vector fields like that, and then boom, match them with their correct graphs. How do you do that?
You plot. You pick a point, plug in the points, and then if it matches the gradient of that point.
Yeah. Keep in mind when a software package graphs a vector field, it's almost always going to diminish the magnitude of the vectors down to where you still have the right direction, but you definitely don't have the right magnitude. See, if I plug in, well, you zoom in so you can see this pretty accurately. If I plug in this vector field, you know, this is only from -2.5 to +2.5 in almost both directions. So you want to plug in something like maybe 1, 1 into one of these. The one that looks like, I'm not sure, this one, because it's hard for me to eyeball. What's handy about this one? There's something really, really handy about that one on we'll see here. What's going to be true about every single vector in that field? If it's
Positive? No.
well, you've got an interchange of y and x, so you can have some sign changes, but if the original components of a vector were yi and xj, and you divide yi plus xj by root x squared plus y squared, what have you technically done to every vector in that field?
Unit vector.
You've unitized every vector. Every vector in this field should be of length 1. And of the 4 shown here, some of them look like their vectors are, you know, some are longer in places and shorter in others. But of the ones here, the one that looks like it has every vector being the same length, looks like it's, yeah, well, I guess that's Roman numeral 1 or I, or the upper left one. Yeah, that guy. So, what do you think would give you this cosine behavior showing up on the graph?
Maybe 3.
Maybe 3.
Kind of looks like a wave.
Yeah. And see, it's kind of hard to tell. What I would think, see, without sine there, and plus, it's also cosine of x plus y, so that really throws a big kink in the cogwork in terms of trying to establish a pattern. But look at the j component. The j component depends on your y values. So what you can do is sort of, the detective work is go for the easier component to work with. See, since my j component is just y, when I'm up above the origin, all the vectors up here, their j value should be positive, which means all these vectors should be pointing up with a positive j. Maybe this way, or this way, but every vector above the x-axis should be pointing up. Every vector below should be pointing down. That is consistent here. Every vector there's up, every vector there's down. Not true here, not true here, not true here. So just because of that easier component to deal with, that kind of helps me narrow that one down to number 2. You see? So it's, but like you said, you know, Isaac. Okay, I'm learning. Yeah, he just suggested picking the point, you know, maybe 1, 1, plugging it into the different vector fields to see which one gives you a vector that, it looks like at 1, 1, you get a vector that goes to the northwest, to the upper left. So if you get a negative I, positive j, when you plug that in, that's probably the more straightforward way to do your matching. But just be careful. This one here looks like it also goes to the upper left at 1, 1, and well, that one might be going down, and that one's going upper right, so it can help you narrow it down at least.
Yeah.
But that's what I mean by matching. Something very similar to this. Okay.
It's like number 3 would be A, because you have all negative x's.
3 would go, okay, yeah, the I component there is the dead giveaway. If your I component's always -1, every vector in this field should be pointing to the left, because you have no chance of the I component going to the right. So rightward movement, rightward movement, rightward movement, yeah. Number 3 has to go with A, or A has to go with 3. So yeah, there are ways to just sort of help you narrow it down. Okay. Then going into line intervals. Let's see. Well, no, shoot. I guess I still want to stand. Going into line intervals, it mentions here that, and again, if you didn't